fifth video in the calculus series. In this one we're going to cover finding the equations of, or that says F, but it should say of cubic functions, and also towards the end will include applications of cubic functions. In general, this would be the form that a cubic function would take. I say in general because, as you've seen from the ones we drew and so on, there isn't always 4 terms from the cube down to the linear. But this is the general format, which you do need to know for the cubic function. And also keep in mind, just like in functions before, however many variables or unknown values you're looking for, that is how many pieces of information have to match to give you that. And that always works as such. And sometimes, and particularly in calculus, the information is not always given directly to you. You have to understand something about calculus to realize that there's almost some hidden information, so to speak. So you have to look very carefully for that. So it's good to know that when you're looking for 3 values, for example, there should certainly be 3 pieces of information that you can use. This is the general format that we use to find the equation of a cubic graph. It is not given to you on the formula sheet. You do need to know it. And it's similar to the one you did when you did quadratics, and the x1, x2 and x3 represent the x-intercepts. So if you are given 3 x-intercepts and another point, you have enough information to find all the values for this function. Your x1, x2, x3 would be the 3 x-intercepts, and then you'd use the other point to find the value of a. So we're going to do one exactly like that now. It tends to be one of the easiest ones that you get. So look at this example. Find the equation of the following graph in the form, and there you can see the full format. We need to find A, B, C, and D, so therefore we should have 4 pieces of information. So we're given the 3 x-intercepts and we are given the y-intercept. So the first thing we need to do is write down the formula that I've just shown you. And each of these factors represents an x-intercept. So we're first going to fill the x-intercepts in. So the first one is -1. So remember it's x minus, so you're subtracting -1, so we have x plus 1. The next one is 2. And the last one is 3. Don't think that you have to start multiplying this out yet, because now we're also going to substitute the y-intercept, the point 0,6. And remember, this is your x-coordinate, your y-coordinate. So every x I see, I'm going to put 0 there, and 6 goes into y's place. So 0 plus 1, 0 minus 2, and 0 minus 3. So we actually have 1, -2, and -3. When we multiply that, we get 6a. Divide both sides by 6, a is equal to 1. So we can then say we have y is equal to 1x cubed. Sorry, I'm jumping ahead of the gun here. I need to go back to this part where I almost had everything except the a, and I need to use the fact that a is 1. So I'm going to just make some space. So if a is 1, I can now start multiplying out, and that will then give me all the values of a, b, c, and d. So I'll leave the x plus 1 in the front, and I'll multiply the other 2 first. Gives me x squared minus 5x plus 6. And now I'm going to continue using the distributive law, timesing the x in the first bracket with all the other 3 terms in the other bracket. And then multiplying the 1 in the first bracket with all the terms in the other. A little bit squashed. Let's collect like terms. Minus 5x squared plus x squared, so we have our like terms there. And then we have plus 6x minus 5x and plus 6. So hence a is 1. B is -4, C is 1, and D is 6. Let's have a look at example 2. G of x is equal to minus 8x plus 20. That is a tangent to the function x cubed ax squared plus bx plus 18 at the point where x equals 1. We need to find the values of a and b. We are looking for two variables, so therefore there must be two pieces of information. And at first glance, this is what I was talking about earlier, you might think there's only one piece of information, that x equals 1. But we need to think what we know about calculus. So first of all, if the point of tangency is where x equals 1, remember what we know about the derivative. The derivative of a function represents the gradient of the tangent at any point. It's not any point in this case. We know the point we're interested in. We also know the gradient. You have to know that the coefficient of x gives you the gradient of the straight line, and in this case the gradient of the tangent. So we're going to use that information. Now let's find the derivative of the function, even though there's a's and b's in it. So 3 times 1 is 3, and that goes to x squared plus 2ax plus b. This is what our derivative function looks like. This represents the gradient at any point, but we know the point that we're interested in, so we're going to substitute it. And we're going to tidy it up a bit, so that is 3 plus 2a plus b. But not only do we know that this is representing the gradient at a particular point, we know what the gradient is. So therefore we have negative 8 is equal to 3 plus 2a plus b. Oh, sorry. So this is one of our statements we're making, and remember we did say we're looking for two variables, therefore we need two pieces of information. So that's my statement number 1 that I have found with an a and a b in it, using the idea that the derivative is the gradient at any point. Now secondly, remember we talked about that when you have a function with a tangent at any point, this point is quite important. It's the point of tangency, and that point is a coordinate that lies on the function and on the straight line. So that's the idea we're going to use now. We're going to try and find out, well, when x is 1, what will the corresponding coordinate be? Now remember we were given the equation of the tangent, so we're not going to use this function. So this point, remember, lies on the tangent and it lies on the cubic function, but we're not going to get very far with our a because our a's and b's are missing. So we need to substitute 1 into the straight line to find out the corresponding y coordinate. So our line is y equals minus 8x plus 20. When x is 1, y will be equal to 12. So we know a little bit more about this now. We know that the point 1, 12 lies on, or is the point of tangency. It lies, so therefore it lies on the straight line and it lies on the function. So let's now use that idea to make our second statement. We have our function, and we know that the point 1, 12 lies on there. So the 12 is the y value, and 1 is the x value. Let's tidy this up a bit. And there now we have another statement, which I'm going to write up here. And as I'm writing it, I'm actually realizing I put an A where I was not meant to in that one. So let's summarize the information we now have. We've now managed to find two statements with the values A and B in. So therefore I hope that it is obvious to you that we are going to be solving simultaneously. So there is our first statement, our second statement. We could even change these a bit more by subtracting 3 from both sides for this one. And doing a similar thing here, subtracting 19 from both sides for the other one. Whether you did it then or later, that doesn't really matter. So remember, in simultaneous equations, our job is to get any variable on its own, and either one of these are pretty easy. It's not that this one is not easy, but if we divide by 2, we'll be working with fractions. So I'm going to work in number 1 and get b by itself. To get it on its own, I'll subtract 2a from both sides. If b is equal to negative 11 minus 2a, I can go and put that into b's place there. So my second step is to replace the b with negative 11 minus 2a. I now have an equation just with a's in it, so therefore I must be able to solve for a. I'm going to add 11 to both sides and divide both sides by negative 1. If I know what a is, I can use it and put it back in here to find b. So if b is equal to negative 11 minus 2a, and a is equal to negative 4, I can now do that to find b. So b is equal to minus 3. So the question was just to calculate the values of a and b. So we have completed that then, stating the values now. So essentially now you have all the knowledge you should need in order to apply that information to cubic functions. You need to have a good understanding of cubic functions and their derivatives. I'm going to start this small section by showing you that 2 cubic functions have been drawn here. The first thing I want you to look at is what the derivative function of each of these would look like. So we're finding the derivative using the rules. And this one as well. First, you should be noticing, or hopefully you've noticed it before, that a cubic function's derivative will always be a quadratic. A cubic function's derivative will always be a quadratic. So now I want to show you a diagram where the quadratic here, the derivative of the function, has been drawn on top or on the same Cartesian plane as its cubic function. So if you notice the colors, the red one, if you're looking here, the red one represents the cubic function. As you can see, it has an x-intercept and then it has a turning point at the x-axis, so therefore there was a repeated factor there, you may remember from before. And then its derivative function, the quadratic, is the one in blue. Similarly on the right hand side, we had a negative cubic function, so that's why it starts by decreasing and it's going downhill here. Also turns on the x-axis, so it must have had a repeated factor. And its derivative function, you can see, has a negative in front, and hence it has this format, is also drawn onto the function. Now the first important point I want to talk to you about is, let's just mark something off here. Notice I'm drawing a line through the turning point of the cubic function. So I'm now going to be talking about these 3 sections that we've made of the x values. But before I do that, I want you to notice that even though I was saying I was drawing this line through the turning point of the cubic function, notice that that also happens to be the x-coordinate of its derivative. Now let's just think about why that is, and I'm hoping it seems quite logical to you. But when we found the derivative, it was a quadratic, and normally if we're drawing a cubic function, we would be making that quadratic equal to 0 in order to find the x coordinates of the cubic function. But if we just see it as a quadratic function, the derivative, if we just see it as a quadratic, then if you were making a quadratic equal to 0, what are you finding? The x-intercepts of the quadratic. So the x-intercepts of the derivative is always the same as the x-coordinate of the turning point. The other thing I want you to notice is that now I want you to focus solely on the red cubic function while I'm talking. In area 1, it is increasing, going uphill. In area 2, it is decreasing. And in area 3, after the next turning point, it's increasing. Now I want you to focus on the derivative function. In area 1, while the cubic is increasing, the quadratic function is, notice, above the x-intercept, so it must be positive, because if a function is below, not the x-intercept, the x-axis, sorry, if a function is below the x-axis, it would be a negative function, because that's where all the y values are negative. So go back to area 1, when the cubic function is increasing, the quadratic function is positive. In area 2, notice now it's below the x-axis, so therefore it is a negative function. So when the cubic function is decreasing, its derivative, the quadratic function, is negative. And you'll see number 3 is now similar to number 1. When the cubic function is increasing, that's going uphill, then its derivative is above the x-axis, so therefore it is positive. Now we'll have a look at the next diagram to see if all of those things hold true again. So again, I am drawing in a line through the turning point of the quadratic, of the cubic. So I'm looking where the turning point of the cubic, the original function, is, and I'm drawing in a line there, and notice again also the x-intercept of its derivative function, the quadratic. Again, we'll talk about these 3 areas. In area 1, the cubic is decreasing, and then at the turning point it changes to increasing, and at the turning point it is decreasing again. Going back to area 1, when the cubic function is decreasing, its derivative is negative. In area 2, when the cubic function is increasing, its derivative function is positive. And in area 3, when the cubic function is decreasing, its derivative is negative. You could also be asked some questions like, for what values of x? They would always start like that. And then it could maybe say, is the cubic function increasing? So you have to be able to look at this function and say, well, it is increasing here. It's always a good idea to highlight, and it is also increasing here. Once you've decided where it is increasing and you've got your focus on that, refocus your attention going from left to right to look at the x numbers. What is missing here, as I'm sure you've noticed, are the arrows, which should be at the end of all of these functions to show that it does go on. So looking from left to right now, we want to look at that green part that we've marked and say, well, what are the x values? Because when you're coming in from your left using your ruler, so you can be running your ruler along here and moving it, and you'll see that the first time you touch the graph is at an arrow. So it must have come from negative infinity, and you stop touching where it was increasing at negative 3. So first it goes from negative infinity to negative 3, and you have 2 choices of how to write that. Either x is less than negative 3, or x is an element of negative infinity until negative 3. So it doesn't matter which way you write that. Let's talk about why it doesn't equal -3. Remember, if it did equal, this would become a square bracket and you'd have an or equal to sign there. But it does not equal -3 because at the turning point, remember what we call it, it's a stationary point. It's neither increasing nor decreasing. Now let's move on to look at the other part of the green. So you would keep moving your ruler, and when you get to this point where x is -1, it starts to increase. But where do you last touch the function? At an arrow, so it must go on to infinity. So your other part of your solution is that x is greater than -1, or x is an element of -1 to infinity. I think try and just use one of those. You certainly don't ever have to write both of them. I'm not implying that. But try and focus on the one that just makes more sense to you all the time. I'm only showing you both because I know you may have been taught a different way. Let's do one more example like that. So for what values of x is the derivative function positive? Now this could even be asked if all you could see is the cubic function. And from what I've discussed with you, you shouldn't need to see the derivative function to know where it's positive, because remember that the derivative function is positive when the cubic, in this case its original function, is increasing. So even if we couldn't see the derivative function, the blue graph drawn here, we should be able to say, well, if we wanted the derivative function to be positive, then its original function must be increasing. So therefore we must be interested in this piece of the function. Once you've decided which piece of the function you're interested in, come in from the left with your ruler, start about there. This is where we first hit where it's increasing, or where the derivative is positive, same thing, and this is where it stops happening. Once you've done that, you refocus your attention on x coordinates. This was a -1 and that's a +1. So in other words, we're looking for all the x numbers from -1 to +1. Remember, when it starts and ends somewhere, your x goes in the middle of your inequality. Those signs will always be less than, because whatever you write here will be less than what you write there. And again, some of you may prefer the interval notation way of writing that. X is an element of everything from -1 to 1. Round bracket because it does not include it, same as the less than sign does not have an or equal to sign. So this is a summary diagram to show you all of the things that we've been having a look at. So notice on the left-hand side we have the function drawn, and on the right-hand side its derivative has been drawn. So there should be a clear mark between those two. So we have the function on this side and the derivative on the right-hand side. When the function is increasing, so going right up to just past the -4 there, when the function is increasing, its derivative is positive. So that's this part of the derivative. And until the point, this one was the x-coordinate of the turning point, and on this side it goes to the x-intercept of the derivative. And then we have this whole section where the function is decreasing, and over those same x values the derivative is below the x-axis, so therefore it is negative. Then we have this area here where the function is increasing again, and for the same x values the derivative is positive. It's really important that you have a good understanding of that. And remember, let's have a quick reminder of why we're talking about the derivative being positive. Remember that the derivative represents the gradient of the tangent at any point. If I drew a tangent here, can you see it's going uphill? It has a positive gradient, and that's why we said the derivative is positive. If I chose this point to draw a tangent, it's when the function is increasing, the tangent is also going down. Sorry, when the function is decreasing, the tangent is also going downhill and decreasing. Therefore, we have a negative derivative. It has a negative gradient. Before we go on and do examples, I know this diagram looks very busy, but focus first on the red. It's the cubic function. its derivative, the quadratic function, and then its derivative, the second derivative, in other words, the straight line is the purple one. And then I've just drawn the line through that to try and cut off the various things. I suppose I should have also really drawn lines here and here as well. So the derivative, the second derivative, has its same connection and relationship to the first derivative as the one we've just been talking about. The quadratic, the derivative of the cubic, the relationships they have are mimicked again and repeated when we are looking at the straight line, the linear function, which is the derivative of the quadratic function. When the now we'll see this as the function this time. When the quadratic is decreasing, notice that the straight line is negative. When the quadratic is increasing, notice that the straight line is positive. And so all of those relationships are important to understand. Right, we're going to do some examples from past papers now. I'm sorry, there's one more thing I wanted to tell you which slipped my mind for a second now that I'm talking about the second derivative. So remember, this is our second derivative. When that is positive versus when it's negative, let's have a look at those two things. So notice that the second derivative is positive here. That's where it's above the x-axis. When the second derivative is positive, what is that doing to the function? When the second derivative is positive, so that's this area here, notice what the function is. It is concave up. And now we're looking at when the second derivative is negative, written like this. Notice what the cubic is doing. So this is where the second derivative is negative over those x values. I was showing this bracket to see that this is where the function is. But then you need to refocus your attention on the x values to see those are the x values where the derivative is negative. Where the derivative is negative. And what is happening when the derivative is negative, so that is here, the derivative is negative there, what is happening to the original function? It is concave down. So just to recap that, when the second derivative is positive, the function is concave up. When the second derivative is negative, the function is concave down. Now we can get on back to the examples. Okay, we have the function given here, f of x, and notice that they have given us the simplified version of it, an almost factorized version of it before it's been multiplied out. First step, calculate the coordinates of the turning point of the graph f. So how do we usually find the coordinates of the turning point? We first need to find the derivative function. We make that equal to 0 because we know that the gradient of the tangent at the turning point would have to be 0. I do apologize. Apparently I think 2 times 4 is 4, but it's 8. We then want to factorize in order to solve for x. And then we get our 2x solutions. X is equal to negative 1/3 or x is equal to 3. Those are our x coordinates of the turning point, but we now need to find the coordinates of the whole turning point. So we need the corresponding y values. So in order to do that, we need to find what the y value is in the function when x is negative 1/3. And we will also need to find what the y value is when x is 3. You'll do these two calculations on your calculator. And for the first one, you should get 500 over 27, but it might be easier to see it as a decimal, especially when you would be looking for it on the Cartesian plane. And the second one is 0. So our coordinates of the turning point is negative 1/3 and 500 over 27, as well as 3, 0. Notice that that is on the x-axis, so it's also an x-intercept, and this should give you a clue as to why that is true, because that factorizes. It's a perfect square trinomial, so you have a repeated factor. Right, we've now been asked to sketch that function, and so what I've just shown is important because we need the x-intercepts. Remember, to find the x-intercepts we make y 0 and factorize. And so you didn't have to do too much work in the factorizing because of the way that this was given in the first place. So x is equal to negative 2 and x is equal to 3. But remember, there's a turning point there. And then to find the y-intercept, we will make x 0, and you can see that if you ignore all the x terms, so to speak, because each of them would be 0, our y-intercept is 18. Let's have a look what that looks like. Remember, the a value was positive, so therefore it's increasing first. This is our one x-intercept, this is another, this is also a turning point. There's our y-intercept of 18, and there's our turning point of minus 1/3, 18,52. Let's go back and look what the other question was. For which values of x will x multiplied by the derivative of x less than 0? So we need to have a careful look at this. So we're looking where x multiplied by the derivative function is less than 0. So firstly, how do we get something less than 0? We need to multiply a positive and a negative value. So when we take an x value and multiply it by whatever the derivative is, positive or negative, we want to get a negative value. So therefore we need two different signs here. So we know that either a negative and a positive would make negative, or a positive and a negative. These could be, so that either has to happen or that has to happen in order for us to get an answer less than 0. So we're going to use that idea now, but we're going to, I think, have to draw it onto the Cartesian plane so we can have a careful note of where we are and what we're looking at. So the derivative function is not drawn on here, and we don't have to find the derivative function and go to all the trouble of finding its x-intercepts and drawing it and so on, because number one, we know the x-intercepts of the derivative function because they go because of the x-coordinates of the turning point. Because the cubic function was increasing to start, therefore the derivative function will be a positive one. Sorry, I'm not sure I went back there. So now we want to try and draw that function onto here. And we know that our x-intercept should be here. So therefore the function would look something like that. And now remember what we were interested in. We want x multiplied by the derivative function must be less than 0. So my red markings here have already cut off where the derivative function is positive, negative, and positive. So in other words, remember the positive is above the x-axis because that's where all the y values are positive. The negative part is anything below. And then let's notice that this is the part, the y-axis is what cuts off the x numbers being negative or positive. So To the left of the y-axis, all the x values are negative. To the right of the y-axis, all the x values are positive. So now let's look at the areas. I'll get a different color to look at that, where we know that we are correct. So my recommendation would be to take a ruler and go from left to the right now, slowly. And as you're moving along, focus on your derivative and the x values and ask where there are two different signs, a positive and a negative. So as you're moving along here, in this area, the derivative is positive because it's above the x-axis, and the x values are negative. So this area is good for us. It is at this red marking that the derivative then becomes negative, and the x values are still negative in that area as well. So this little area here is not good. Once we go past the y-axis, our x values are positive and our derivative is negative until here. So this area is good for us as well, and after that on this side the derivative is positive and the x values are also positive, so that's not good for us. So now we have to look how we're going to write the parts that are ticked. So all the x values up to here were good for us, we wanted those. And then from here to here as well were good for us, we wanted those. So the first side are all the x values less than negative a third. Can't be or equal to, because then the answer would be 0 and there was no or equal to here. And then for this part between here, the x goes in the middle, less than either side, to show that it starts and ends somewhere. It starts at 0 and ends at 3. I was going to do 4 videos, but this video has become a bit long, so I think in the next video I'm going to do 3 other, I think I just said I was going to do 4 videos, I meant I was going to do 4 examples. So in the next video I think I'm going to do 3 full examples, continuing to apply your knowledge of calculus and cubic functions.